Okay, so 11.2 here, we're going to be finding areas of regular polygons. So let's do a little warm-up review and talk about a triangle here. And let's say triangle HKJ is equilateral. Okay, because again, to be regular, it means that all side lengths and all angles are the same. Okay, so the triangle itself, right, the big triangle, HKJ, is a regular triangle. That's an equilateral triangle is regular, so all side lengths are 10 because they gave us one of them, right? Okay, and all angle measures are equal to each other. So we know that angle, and then the top angle are all equal. And in an equilateral triangle, in any triangle, the angle sum's 180, right? So if all three angles are the same, we know each angle must be 60 degrees. Okay, and that's going to mean for us that these little angles up here, right here and right here, are each 30 degrees because we had two angles that formed the big angle H was 60, so they're each 30. And then we also know that the bottom, the base of the triangle KJ is 10, so that means that K through M must be 5 and M to J must be 5 as well. Okay, so let's see if we can get all the pieces we need here. Oops, that kind of overlapped there. All right, so KJ, we know KJ is 10 units. Okay, we saw that because again, the triangle is equilateral, so they are all the same. Measure of angle K, all the angles in an equilateral triangle are 60 degrees. Okay, KHM, so KHM from here to here, that was one of the two pieces that made a 60-degree angle, so that had to be 30 degrees. Okay, now the part HM, the segment HM, I should say, it's actually called an altitude of the triangle, right? It's perpendicular to the other side. Now that one's not necessarily 10. Okay, we know the side lengths of the triangle are 10. So let's draw the picture here. We have this, and then here is HM right here. Okay, and we need to figure out that length. Okay, so I just kind of took the left side of the triangle there. We knew this length over here was 10. We knew this was 5. Okay, this was point K right here. We knew that angle was 60 degrees. That's 90. This is point M. This is point H. And we need to find that side length right here. Okay, so there's a couple things we could do. We could either use trig. I guess they both involve trig. I mean, we could use like SOHCAHTOA trig. Or, if we remember, that angle there is a 30-degree angle. This is actually one of our special triangles, right? The 30, 60, 90 triangle. And just to refresh ourselves, with the 30, 60, 90s, the way it goes, let's see if I can try and draw it the same way here. There's the 30, 60, and 90. The short side is always x, okay? The hypotenuse, if you remember, was always 2x. And then the middle side was x root 3, back when we derived the special right triangles. We kind of did it from an equilateral, actually, and then did Pythagorean theorem. But that's actually the other option here. We could have just gone straight to Pythagorean theorem since we knew 2 out of the 3 sides. But this was a little quicker if you remember it, okay? So basically the 5 down here is like matching up with the x, right? And the side that we want over here is always the short side times root 3. So it's just going to be 5 times the square root of 3. Okay, and if you want to get an approximate from a calculator, I worked it out as about 8.66, and that would be what you would get if you did the Pythagorean theorem on it, which is probably an easier way. But I just wanted to refresh some of the trigonometry because it is going to show up a little bit here and there, definitely in your future math classes. Okay, so just a little review there. We'll be using some of this stuff to get some areas. Remember we did the last one, we had a 5 down here, and then this side ended up being 5 times root 3. Okay, so let's use that those properties to get a formula here. If we need the area of an equilateral triangle, okay, again, if you think about the area of any triangle, the little triangle down there, so the area of a triangle is always 1/2 times the base times the height, okay? So let's see what we can figure out here. We clearly know the well, they're telling us the length of the side is S, right? It could be anything as long as all three sides are the same. Okay, so we have 1/2 times whatever the side length is. Now the issue is this h, this height of the triangle, is this piece. Okay, and that's very similar to what we were just finding in the other problem, and that's why we did it. Because again, remember, this is a 60-degree angle. This little guy up here is a 30-degree angle. Okay, and if the entire side length is S is from there to there, very similar to what we saw in the last one, that, let's see, it would be half of that would be there to there. Okay, that's an S over 2. And we just saw that the side length, in this case the one that we labeled H, is always just times the square root of 3 large. So similarly, if our short side is S over 2, right, that's the shortest side because it's across from the 30, I know this leg here is going to be that length times the square root of 3. So it's going to be S over 2 times the square root of 3. Let me rewrite that. It looks like a 5 up there. But that is an S. Let's see. There we go. I don't know if that looks any better. So that's an S, okay? The side lengths are all S. And if we just want to do a little simplification, like multiplying this all out, okay, if we see the numerator, I'll just throw a 1 under there so we have fractions. The numerator is S times S root 3, so that's S squared times the square root of 3. And then in the denominator, there's a 2 times 1 times 2, which is just 4. Okay, and this is going to be our formula. That's going to find you the area of an equilateral triangle. And the key, again, is that the side length is S. Okay, so if you just take a side length squared times the square root of 3 over 4, it's going to be a shortcut formula. And again, write this down. I'm not expecting you to memorize all these formulas and whatnot, but just have it written down. If you see a question that asks for the area of an equilateral triangle, that's the formula we're going to use. So let's go ahead and set one up. Here we go. Here's one. We need to find the area of a triangle with sides of 10 centimeters. Okay, so they're just telling us the sides are 10, so I'm assuming all three sides are 10. It's equilateral. Okay, and we have the formula now. We don't even have to do any magic work or anything. We don't have to do the 1/2 base times height and find the height and all that stuff, because this formula that we just built takes it all into account. So again, the area, if it's an equilateral, only if it's equilateral, okay, is S squared times the square root of 3 over 4. So we have a S, or a side length of 10. Okay, so 10 squared is 100 root 3 over 4. Okay, and that would be like an exact value. If you wanted to get a calculator, it might be a little more useful of a number if you actually calculate it out. I'm getting around 43.3 centimeters squared, okay, just by multiplying all that out. Okay, so that works for equilateral triangles only, okay? Otherwise, it's just 1/2 base times height, and you'd have to work some way to find the height, maybe using Pythagorean or using some trig and whatnot. If we want to extend it beyond triangles, you know, what if we have a pentagon or an octagon? And as long as it's regular, this whole section is about regular figures, okay? Side lengths and angles are all equal to each other. Let's kind of build up on how to get that done. So the center and the radius of a polygon, okay, are the center and radius of the circle that circumscribes it. So you see there I have a 1, 2, 3, 4, 5, 6, well, it's 6-sided, and that's a hexagon. And there's a green circle circumscribing it, right? So the center of the polygon is the center of the circle. And you see the radius there, those dotted lines from the center which go to the vertex. That is the radius of the polygon. Okay, now there's this other term that we're going to use, okay, called the apothem. Okay, not like an opossum, like the animal, it starts with the A, P-O-T-H, apothem. It is the distance from the center to any side. So when we measure to a side length, we're going to go straight down and make sure that it is perpendicular. Okay, that yellow segment that I drew is what we call the apothem, and it has a length. Okay, and we're going to use that length along with, if you see over here, S is the length of each side in the polygon, just like it was for an equilateral triangle. Okay, so the idea is, here's the diagram again. You see the yellow segment there again is the apothem, and S is the length of the side. Okay, so like an entire side of the polygon, each one is S. Okay, and the area, if we want the area of the polygon, it's going to be the area of each triangle. Okay, so you notice there's a triangle here, right? Times the number of triangles. Okay, that should make sense, right? If there's 1, 2, 3, 4, 5, 6 triangles inside there, if we found the area of one of the triangles and multiplied it by 6, that would give us the entire area. Okay, so let's think about how do we do that. The area of each triangle, again, is 1/2 base times height. Now in this case, the base of the triangle is that S value, whatever the side length is of the polygon. And the height is this new thing we're calling the apothem. I'm going to just abbreviate that with A. That's going to be the length of the apothem. So we'll use A for that. And then times the number of triangles. And we're just going to call that N. Okay, in this case it would be 6. It's the number of sides of the polygon equals the number of triangles that there are as well. Okay, so 1/2 S times A times N. Okay, so let's do an example. Let's say we have a glass, okay? It's a 12-gon, okay, 12 sides. Each side length is 1.2 centimeters, and the radius is 2.3 centimeters. Let's suppose we need to find the area of the bottom of the glass. Okay, let's see what we can do. All right, so the again, the 12-gon here it would have 12 different triangles, right? We take from the center to each of the vertices, and there would be 12 of them because there are 12 sides. What we're going to do, we're going to find the area of the yellow shaded of one of the triangles, and we are going to then multiply that answer by 12. Okay, so let's see what we can do. So I tried to, let's see, this triangle right here, it wouldn't let me shade it yellow just to show that it's the same triangle, but it is just, you know, expanded and enlarged, I should say, out there. Okay, so let's use that so we have a little room to work. You see the 2.3 are the radius, the 1.2 is the S value. So each side on this 12-gon is 1.2 centimeters. So the base of our triangle is 1.2 centimeters down there. Okay, so let's see, can we find that apothem, which is the dotted line here? Okay, because we need to use that. That's going to be the height of each triangle. And we need to figure out what that is so we can find the area of the triangle and then times by 12. Okay, so let's think about with that triangle, if the whole base is 1.2, I know that each one of these is half of that, right, or 0.6. Okay, so we really have, let me just draw this even smaller piece of this. We have 0.6, we have a 2.3, okay, and then this over here is this dotted line here, which is the apothem. I'm going to call that A, and let's see if we can find that value. Okay, and again, we do have a right angle, that's important. We can use the Pythagorean theorem, right? So we can say something like A squared plus 0.6 squared must equal 2.3 squared, right? Just old Pythagorean theorem. Okay, 0.6 squared is 0.36, and 2.3 squared is 5.9. Okay, if we subtract over, subtract 0.36 from both sides, I'm going to get A squared equals 4.93, and taking the square root, A is going to be approximately 2.22. Okay, so that is the apothem, right? That's the height of each triangle, it's the apothem. Okay, so what we can do now, what we have to do is find the area of one triangle and then times it by 12. Okay, so let's see how that looks. So the area of each triangle is 1/2 times the base. Okay, the base again, the base of the triangle is the 1.2. The height of the triangle is what we just found, which is 2.2. Okay, that's that formula 1/2 times S times A. That equaled about 1.332. Okay, that's the area of one triangle. Okay, that's this one right here, or any of them, right? Any triangle, they're all the same size. That's the area of that. So the total area of the entire 12gon, we just need to multiply by 12. We need to take the 1.332, multiply it by 12 because there are 12 triangles, right, all the way around. And when we do that, we get a final answer of 15.98 centimeters squared. Okay, so that's the area of the base. So if this was a glass and you needed to know the volume or something, it would probably start out by finding the area of the base like we just did and then multiply by the height to get the volume or whatever. But what we just found, okay, was the area of the entire figure. Okay, so all the way around, 12 gone, 12 little triangles. Okay, we found the area. Pretty cool. All right.